let's pretend I didn't just say this. So, so we're gonna start today, but by let me just start by reminding you of this formula that we proved last time. That the number of permutations of the numbers from 1 up to n, with descents precisely at positions s1 up to sk, was given by this strange determinant. So we proved this with the inclusion-exclusion formula, and it might be the first time that you see a combinatorial problem with the answer is a determinant. But what I want to do today is that I want to show you that actually this is just part of a bigger theory of really why determinants appear in combinatorics. They really appear in a lot of places, and we have a lot of fun with them. Actually, that's going to be the name of the class today. Fun with determinants.
I have a question.
Yep.
Do you think that's because the definition of the determinant is itself like on permutations?
Definitely, the fact that the determinants are defined in terms of permutations is going to play an important role. But I want to show you a very concrete setting that's pretty general where determinants appear in combinatorics. Does anybody get the reference, by the way? So our Dean Sheldon Axler, who we talked about how I talked a couple of classes ago how he likes to teach linear algebra without determinants, because it's true that a lot of linear algebra can be done without determinants, and his point of view is that it should be done without determinants whenever possible. And I agree to some extent with that point of view. Anyway, so he has a paper that's very famous. I think it even won like some expository paper award, and his paper is called "Down with Determinants." So actually, it's an interesting paper. You should read it. But today we're going to do exactly the opposite. We're going to actually embrace determinants and see that they really play a very important role in combinatorics. Okay. So let me start by taking this formula and do some manipulations to make it look a little bit different. So let's see, how do I do this? For example, one property of determinants that is very important is that they are multilinear in the rows or the columns, meaning that if I am to multiply, let's say, this column by a constant, then the determinant will be multiplied by that constant. Okay? And so one thing I'm going to do is I'm going to take this n factorial and I'm going to bring it to the last column. Okay? Instead of having it outside, I'm going to put it here in the terms of the last column. And I haven't changed anything. Okay? And so what I did is multiply this column by n factorial, but actually I also want to multiply each column by something. Okay? What I'm going to do is I'm going to multiply this column by s1 factorial, this one by s2 factorial, this one by s3 factorial, etc. Okay? So let me take this one multiplied by s1 factorial. And now, of course, if I multiply here, then I just scale the determinant by s1 factorial, so I should divide by s1 factorial. Okay? So I multiply this column by s1 factorial, and so I should divide by s1 factorial so that I don't change the answer. Okay? But actually, what I'm going to do is I'm going to take this 1 over s1 factorial and bring it into this row. Okay? So I'm going to take this thing, and instead of multiplying it outside, I'm going to multiply it in this column, in this row, I'm sorry, which is not going to change the result. Okay? So I take it from out here, and I bring it in here. So I divide by s1 factorial, this disappears, and I get a 1, and now I get s1 factorial here, s1 factorial here, s1 factorial here. And maybe you see why it is that I'm doing this. Maybe you can begin to see what I'm after here. Okay? S1 factorial over S1 factorial is 1. Anyway, let's just leave it like this. Now again, let me multiply this column by S2 factorial. Okay? S2 factorial, S2 factorial, S2 factorial. And so now I multiply the determinant by S2 factorial, and so let me fix that by dividing this row by S2 factorial. Okay. So this goes back to 1, and now I get S2 factorial here, S2 factorial here. Okay. And I keep doing this. So I multiply this by S3 factorial, okay. S3 factorial, S3 factorial, S3 factorial, and so on, and then I divide the row, which is this one. I didn't write it, but I would divide this row by S3 factorial. Okay. And so you see, when I keep doing this, when I'm done, what do I get? I actually get a bunch of binomial coefficients. Everything you see here is a binomial coefficient, especially if I put this here. 0 factorial is 1, so that doesn't change anything, and now I just get a bunch of binomial coefficients. Okay. So let me rewrite this as S1 choose 0, S2 choose 0, and so on. S3 choose 0, up until n choose 0. Okay. Now this is S2 choose S1, S3 choose S1, and so on. N choose S1, and I keep doing that, okay? So S3 choose S2, here I get N choose S2, here this is, oh, I forgot, I should have divided this by SK factorial, so that here I get N choose SK, and why not take these ones and call them S1 choose S1, S2 choose S2, so on. Okay. Yeah.
Can you reassure me that this is actually what we have? Because in the beginning, you start off with bringing the n factorial in, and then the S1 factorial popped up, and then you brought that back in, and then technically something pops out, and you bring that back in.
So you're worried about that n factorial? That maybe I cheated you on that one term.
Well, I'm afraid there's something left over that maybe it's not all encompassed here.
Yeah, it's a very good point. So, and I'm gonna ask you to rewind mentally in your head now. So what did I do? I multiplied this by n factorial, this by sk factorial, so dot 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 s3 factorial, s2 factorial, s1 factorial, right? So I multiply by this stuff. And what did I divide by? I divided by 0 factorial, s1 factorial, s2 factorial, up to sk factorial, which is what I forgot to do, but I need to divide by sk factorial. Okay? And so you see what happens is that I borrowed this n factorial, which was outside, and you're right that there was something left over, but it was the 0 factorial, right? And that's why this computation works out. Okay, so we get this determinant, and now maybe it looks a little bit nicer. And let's even take this 0. I mean, you see a pattern here that over here, I mean, here, these are all S1 choose something, so I could write this S1 choose S2. Right? S1 choose S2 is 0 because S1 is smaller than S2, but that now goes with this pattern, and so I can do it with all of them, right? And so here I can write S1 choose Sn, S2 choose Sn, oh, S2 choose Sk, sorry. S3 choose Sk, and so on. Okay? And so I get this square matrix of binomial coefficients. And I'm claiming that I'm not claiming, we proved that this determinant is equal to the answer to this combinatorial problem. Okay? And so now I want to think about generalizing this phenomenon. So, more generally, let's consider this determinant. Let's consider the determinant of a square matrix where right here the ij entry is sy choose sj. And now I'm going to consider the square matrix where the ij entry is ai choose bj. So here these are any integers. Okay, I have some increasing list of integers, and then I just make a table of binomial coefficients just by saying like I did here. I guess maybe it's the transpose of this, but yeah, I guess what I wrote here is the transpose of what I wrote here. I'm saying in row I, put on top the numbers A1, A2, A3, etc., and then make them choose B1, B2, B3, etc. Okay. So I get these AI choose BJ. I get a square matrix of binomial coefficients. Okay, and so this is I don't know. We might call these binomial determinants. Okay. Now, as I understand it, actually the history is not that we started with this and then we decided to generalize it. It's that these determinants appeared in algebraic geometry. And if you can look in the notes, I have the reference to this paper by Alain Lascaux on Chern classes of tensor products. And this determinant appeared in a formula as with some kind of algebraic geometry interpretation. And as I understand it, I wanted to have a look at the paper before class, but I didn't get a chance. But as I understand it, the point is that this number was the formula for some algebraic geometry invariant, which is positive by definition. I think it's probably, the way these things usually work is that it's the dimension of some vector space or something like this. Okay, and so in that computation, this number appeared as the dimension of something, and therefore it's a positive integer. Okay, but I hope you realize that if you look at this, there's no reason to believe that it should be positive, or it's some determinant, right? It's a sum of n factorial things. It's completely unclear whether it's going to be positive or negative. Okay. And I already told you that one instinct that we have as combinatorialists is that if we see a positive integer, we want to know what it counts. Okay. And so what I want to address next is what this counts. This is what Gessel and Viennot were after. Why are these positive? What do they count? And of course, it should be something more general than this, right? This is a special case of this. So we're going to talk about some more general problem. Okay. This is one of these situations where actually I think the generalization is much nicer than the special case. We're going to see that the answer to this is extremely elegant. And so, in the process of answering this question, Gessel and Viennot discovered what is usually known as the Lindström-Gessel-Viennot lemma. So Gessel and Viennot were trying to address this problem. Lindström, I think a little bit earlier, had discovered the same lemma in matrix theory. But actually even earlier, Carlin and McGregor. How do you spell McGregor? I think with an A this one. Oh no, with no A. McGregor in the 50s had discovered this, and I think they were probabilists. Somehow, these are always the names that get associated to this, but I think these are the first ones who discovered this. It goes like this. Let G be a directed graph. Okay? And let's assume that it has no cycles. And actually, while I do this, I'm gonna do an example. So just try to remember in your head what this looks like. I'm gonna erase it, and I'm gonna come back to it later, but it takes up a lot of space, and I'm not gonna want to write it down again. So we have a directed graph, okay, and so it might look like this. Okay. And imagine that all the edges are pointing down. So that's an example of a directed graph. Every edge is directed down, and notice when I say that there's no cycles, what I mean is that there's no directed cycles. Okay, so this graph, if you ignore the orientation, it does have cycles, but you can't really go around the cycle. You would have to walk along some edge in the incorrect direction. Okay. Consider vertices S1 up to Sn, which we're going to call the sources, and T1 up to Tn, which we're going to call the sinks. So in this case, this is going to be S1, S2, S3, and this is going to be T1, T2, T3. Okay? Now, assume that all, maybe I'll call this set S and T. Okay. Now, let's consider the routings from S to T. And what's a routing? A routing is a way of kind of choosing paths for the vertices from the vertices in S to the vertices in T. Okay, a routing is choosing routes from S to T, and these routes should not intersect. Okay. So a routing from S to T means n vertex disjoint paths. From S to T. Okay, so an example of a routing. The routings have to go in the direction of the edges of the graph. So I might take, for example, S1 over here, S2 over here, and now from here, I have to make sure not to hit this guy because I would be hitting that vertex, so I have to go this way. And so this is an example of a routing from S to T. Okay. So I'm going to assume that all the routings from S to T join or send. Question?
Do we always want each routing to have so that the source node maps to its corresponding sink node based on the indices?
So this is what I want to assume, exactly. So I'm going to assume that in any possible routing that you have, you must map S1 to T1, S2 to T2, S3 to T3. Okay. And this is a property that the graph might or might not have, but you see in this example it is true, right? That if you want to send, if you want to connect the S's to the T's without intersections, the only way to do it is to send S1 to T1, S2 to T2, S3 to T3, right? Because if you send, let's say, S1 to somebody else, then you need to send somebody else to T1, and those paths would have to cross. Okay, so this is a property that the graph might have, and if it does have it, then the determinant. Oh, I forgot to say. So let Aij be the number of paths from Si to Tj. Okay. So for every source and every sink, you get a number which says how many ways are to go from Si to Tj. And so that means that I have a square matrix, right? And so if I consider that square matrix, for every I and j, I look at the number of paths from Si to Tj, and if I take the determinant of that matrix, okay, then what I'm going to get is precisely the number of routings from S to T. Okay? Yeah.
So these Aij are 0 if I and j are not. From what you're saying, that Si has to be sent to Ti.
No. So you see, I should have said this before I said the part about the routings, and then you wouldn't be confused about this. So you just have your vertices Si, your vertices Tj, and now for every Si and every Tj, you just let Aij be the number of ways of walking from Si to Tj. And this is some number for every I and j. Like here, like for example, from S1 to T2, there is one way to get here. So A12 would be 1. A13 would be 0. Right? You cannot get from. Actually, I mean, let's do it real quick. Let's do it real quick. So we're making a matrix where the rows correspond to the Si's and the columns correspond to the Tj's. And then I say, how many ways are there to go from S1 to T1? Well, you either go this way or this way. From S1 to T2, there's only one way. From S1 to T3, there are no ways. From S2 to T1, there's one way. From S2 to T2, there's two ways. From S2 to T3, there's one way. From S3 to T1, there's no ways. From S3 to T2, there's one way. And from S3 to T3, there's two ways. Okay. So that's some matrix, and then what I claim is that if I compute this determinant for, I did it ahead of time. Then this 4 is precisely the number of different ways of routing the S's to the T's. Now, this green thing that I did is one of the 4 ways, but there's 4 in total. Okay. And so this gives you a very natural context, but the determinant is just a natural answer to some routing problem. Okay. Yep.
Are we using the assumption here that we're only sending S1 to T1 and S2 to T2? Where would that come in?
Let me make some comments about that actually, because this statement is a little bit. So this is a special case, but let me make some comments about this. So the first comment is that we made this assumption that there's no cycles. Actually, no, let me start with a more important comment, which is that this also works for weighted paths, for edge, for G with edge weights. Okay, so it might be that in your graph G you associate a weight to each edge, okay? And then if so, then you define Aij to be the sum over the paths from I to j of the weight of the path, where the weight of a path is the product of the weights of the edges. Okay? And so what does that look like here? Well, I want you to now imagine that we gave a weight to each edge. Okay? And it doesn't really matter what weight I give it, so let's say this is A, B, C, D, E, F, G, H, I, J, K, L. Okay? So then now, for example, what is S1T1? So what is this entry here? There's two ways of going, this way or this way. Right? And this edge has weight, this path has weight A times G, and this one has weight B times H. And so you do that for every one of these entries. And then the result is that when you compute this determinant, then what you get is sum over the routings of the weight of the routing. Where the weight of the routing is again just the product of everything. Okay? And I thought that this would be clearest if I did an example. So again, we're going to do the high-tech thing of turning the camera, because I actually computed this example ahead of time. Oh, thank you. Yeah, I noticed last time I did this, something was in the way, but not today. It looks like it's visible. So, okay, so those of you that were in the room were probably wondering what this thing was. And you see what I wrote here is precisely the matrix of paths for that graph. Right? So this is my AG, my B plus BH. Now if I want to get from S1 to T2, I have to take edges B and I. If I want to get from S2 to T3, I have to take DK, and so on. Okay? So this is the matrix given by the paths from each SI to each TJ. Okay? And so the claim is that when I compute this determinant, I should get precisely the weights of the routings. Okay, and so I did this ahead of time. I multiplied all of this out. Now let's talk a little bit about how I did this. So I went down the main diagonal, right? So I need to multiply this times this times this. Now you see this is a binomial, 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 which means that there's going to be 8 terms for multiplying this and this and this, right? Which is choose something here, choose something here, choose something here. So I did AG times CA times EK, AG times CI times FL, and so on. Okay, those are these 8 terms. And this is the main diagonal. Okay. Then I went this times this times this is 0. This times this times this is 0. So there's no more contributions in this direction. And now when I come over in this direction, I get that this times this is 0, and then I guess I got this times this, so AG, BG dk EJ, BH dk EJ, and so on. So I did it all and I got this stuff. But what I want you to notice now, I mean, this doesn't quite look like this, right? In particular, it has positive and negative signs, where this formula only has positive signs. So is there some cancellation here? Well, there is, at least if I did everything correctly. So, for example, this minus right here, AG dk EJ, is the same as this right here. And similarly, BH dk EJ should be somewhere
Middle, right?
here. This guy should be somewhere. BICHEK is here. And this guy is this one. Okay. And so what do I get? I get 4 terms, and that's why I knew that the answer was going to be 4 here. AGCIEK. Well, actually, if we draw that here, see, AG CIEK. Right? This is actually this. I think this green is a little hard to read. So this is actually this routing. AGCIFL is this routing. AGDJFL is this routing. And BHDJFL is this routing. And everything is cancelled out. Okay, so the magic here is that everything cancels except for the routings. So you get precisely the routings. Okay. Now, why is it that these things cancelled out? It's not an accident, of course, because this theorem is true. Can't be an accident. Let's look at this guy, right? Why did this guy cancel? What is this AG dk EJ? Where did it come from? It came from AG. And actually, I want to use 3 different colors because this is a product of 3 paths, right? AG dk EJ is the product of the path AG, the product dk, which goes like this, and the product EJ, which goes like this, right? These are the 3 paths that contribute this term. Now, I cancel this one with this one. So where did that guy come from? It came from AG, which was this path, then DJ, which was this path, and EK, which was this path. Okay? So then you can see why they cancel. I mean, the colors are different, but the terms are the same. And so they have the same weights. And this already gives you an idea of how we can prove this fact. It's basically to show that whenever you have a crossing, that's going to induce some cancellation. That's going to be the idea of the proof. Okay. Before I write down the proof, I want to make 2 other comments. One, that I said I had no cycles, but actually there's a way of dealing with cycles. So there is a version with cycles. And also, I made this assumption. But there's also a version without this assumption. So there's a version where our routing doesn't have to be straight, let's say. Where you don't have to map SI to TI. Okay, so I'm going to prove this in this version that's slightly simpler, but But there are, if you ever need this, there are versions that deal with cycles and that deal with things not being lined up left to right like they are here. Question?
In this example, we're fixing the number of source nodes and sink nodes. So I'm wondering if we have some directed graph G and we fix the number of source and sink nodes at random, and we label them at random, whichever ones are going to be S1, S2, S3, and so on. Is there like an upper bound for the number of routings?
Actually, that's a really good question that I was trying to decide whether to talk about tomorrow or not, and I haven't decided. But the question is basically how many roads fit in this graph. Right? Like here, I could have routed only one S to one T, or I could have routed 2 to 2. I could have routed 3 to 3, but you can. But if I'm understanding your question correctly, your question is, if you have a big graph and you choose some sources and you choose some sinks, it's not necessarily the case that you can find a routing from all the sources to all the sinks. And the question is then, well, how many can you route? Maybe you cannot route all of them. So what's the biggest number of routes that you can do? Okay. And this is a really good question, and this has to do with something that some of you might know called the max flow min cut theorem. How big can a flow through the graph be? Basically as big as the smallest cut that you can make to it. Okay? So yeah, I haven't decided if we're going to talk about that next time or not, but in case we don't, it's a very interesting question, and you should look up max flow min cut. Okay, so let's prove this theorem. Are there any other questions about how I did this? I'm about to reorient the camera. So. Okay, so here's the proof of the lemma.
Super quick question.
Yep.
So is this going to prove into something bigger? Is that what it's called a lemma? Or
That's another good question. Why is it a lemma? If I don't know, it's cool, right? It seems like it should deserve to be called a theorem. Actually, I was reading. Maybe some of you know this book called Proofs from the Book, written by Eigner and Ziegler. So it's the story of Paul Erdős was one of the most famous combinatorialists, and he always said that God had a book with all the perfect proofs of various mathematical theorems. And so whenever he had a proof but he didn't like it, he would say, well, this is not a proof from the book. We still have to keep working to figure out what the proof from the book is. And okay, so there's this book, and it's called Proofs from the Book. The proofs in there are good. I mean, it's a book of very nice proofs. And they discuss this, and they make this comment that I think is very funny, which is that they say that every mathematician's biggest aspiration is to prove a lemma. Because there's very few lemmas, like the Gauss lemma, or the Eisenstein lemma, or the Lindström-Gessel-Viennot lemma. There are things that maybe the proof is not so terribly difficult, but they're extremely powerful, and so they get used a lot, and yet they're called a lemma. So it's kind of like a very simple observation that's extremely powerful. So I think it's called a lemma because the proof fits on one board, but that doesn't mean that it's not important. And it's a good book, actually. I recommend it if some of you are looking for some fun math books to look at. Okay, so let's figure out what this determinant is. Okay. So how do you compute a determinant? You're supposed to take the sum over all permutations of Sn of the sign of the permutation and then A1 comma pi of 1, A2 comma pi of 2, Am comma pi 1. Okay? So now, let's do this. So we'll leave that sign alone, but we know what this is, right? So this is, by definition, is the sum over all the paths P1 from 1 to pi of 1. Okay? I'm trying to keep the notation a little bit cleaner, but really what I mean is from S1 to T pi 1. Okay, but you should just think that this is the vertex 1 on top and the vertex pi of 1 in the bottom. Okay? And weight of the path. This is this guy. They all look like this. So path, and the weight of that path.
Question.
Yeah?
So what do you mean? Because here there was when you wrote it down, you didn't talk about weight.
Oh yeah, so actually, one reason that I wanted to discuss the weighted version is that it's easier to prove. Sometimes proving something more general is a little bit easier. And actually, I think you see that here, because here you can actually, this kind of reads off what the proof should look like. I mean, you actually know exactly what the 4 routings are, and they come with names, right? And so the more general statement is going to be a little bit easier to prove, actually. Okay, so what do I do now? I do this. I say, well, this is the sum. Now, you see, I'm basically looking at all the ways of taking, some path from 1 to somebody, some path from 2 to somebody, etc. And so, let me just sum over all n. Let me call P the collection of P1, P2 up to Pn. Paths from S to T. Okay, and so these are n tuples of paths that start at the top n vertices, end at the bottom n vertices, but they might do it in some weird order. Okay, they might map the first guy to the 5th guy and so on. Okay. And the point is that really here I'm just multiplying all the weights of these different paths, and so I just get the weight of. Let me just define the weight of P to be the product of the weights of the paths. Okay? And that's again what we were doing in this example kind of naturally, right? We were just multiplying weights of paths, and that became a weight of a collection of paths. Okay? So here this product gives me this weight, but now I can't forget about the sign. Okay? And the sign, well, I'm not indexing by pi anymore, but the thing is that just from looking at the paths, you know what the permutation is, and so I can just define, you can just call this the sign of P. The sign of P is just the sign of pi. Okay. So if P happens to map S1 to T1, S2 to T2, etc., then this is 1. But if it maps according to some other permutation, then you put the sign of that permutation. Okay. And what are we summing over here again? We're basically summing over all the collections of n paths. So like this might be one path, this might be another path, and this might be the third path. Okay? We're summing over all ways of doing this. So, what do we do next? We're just going to make some observations. Okay, so first of all, every routing appears here. Appears. And what's a routing? It's something like this. Every routing is one of the terms, right? And like I said, because this maps Si to Ti, we get the identity permutation, and so it actually comes with a positive sign, which is how I want it. Okay. So every routing appears with the correct weight, and what I have to show is that everything else cancels out. So let's consider a non-routing, like the one that I drew over there. So I'm claiming that this guy should be cancelled out. So what I'm going to do is show another routing, another non-routing, I'm sorry, that cancels it out. Okay? It's going to be this one. So what I'm going to do is this. I'm going to say, okay, this is not a routing, so some paths cross. Right? Some Pi and Pj must cross. And so what I'm going to do is that I'm going to just point to one crossing that I'm going to say is the first crossing. And the way I'm going to do that is that I'm going to go from left to right, and I'm going to say, does anybody cross this first path? Right? And the answer is yes, the first path was crossed, and it might be crossed several times, so let me look at the first crossing. Okay? It's this one. So let me say that again. I look at the first path. If the first path didn't cross anybody, I move on. But if the first path did cross somebody, then I look for the first crossing that appeared and I circle it. And if the first path didn't cross anybody, then I look at the second one, then the third one, until I find the first time that happens. Okay? And what I want to do is I just want to change the non-routing a little bit. How do I do that? Well, given that the answers that it should take place there, it seems clear what I should do is just kind of flip right here, right? So this other path is not involved. I leave it alone, okay? And I just reroute traffic here. I say, this guy, let me go to the intersection and send it over here. And this guy that was coming over here, let me reroute it and go over here. Okay. So I just reroute in this intersection. Okay. Yep.
So can't routings exist without intersections, but they're not like straight routings? Doesn't it depend on the graph?
So this is where I'm using this assumption that the routings do go from Si to Ti to prove this version of the theorem. And that's why I really am saying, if it's a routing, then it goes straight like this. Maybe I'll say a little bit about when that doesn't happen later. Okay? But if I do assume that the only routings have to be straight from Si to Ti, then they have to look like this. And then what's the point? The point is, look at this guy and look at this guy, right? So these guys clearly have the same weight. And I'm claiming that they cancel, which means I should show that the sign is the opposite. So why is the sign the opposite? Well, the sign is the opposite because all I did is do a transposition to the permutation. And when you change the permutation by one transposition, it goes from positive to negative or negative to positive with the opposite sign. And there's one more comment that I should make, which is to say, well, okay, so maybe you said, I tried to cancel this one with this one, but what if you wanted to cancel this one with somebody else? Okay? But the thing is that, look at what happens when I try to look for who should cancel this guy. I'll say, let's go from the first, look at the first path, does it intersect anybody? And I land at the same intersection, right? And when I try to see who should cancel with this guy, I'm going to get this guy. Okay? And so I really get a pairing. They really get paired up into pairs where one is positive and the other one is negative. Okay? And that's why the terms that should survive, survive. The terms that should not survive occur in pairs that are plus and minus and disappear. And this is what we saw in that example. Actually, I encourage you to look at that particular example and look at every single thing and what canceled, and you'll see this in action. But this is the proof. That's it. So you see, it did fit, not even in a full board. So it's a cute proof. It's simple. It's not terribly difficult, but it is a very nice insight. Okay? And you have to know what you're trying to prove in order to prove it. So this is the Lindström-Gessel-Viennot lemma. Okay. Now just to make let's make some comments about what if this condition is not true. What if it's possible that there are routings that are routings, they don't intersect, but where S1 goes to T2, S2 to T3, etc. If that's the case, then what the same proof shows is the same statement, except that I guess I didn't write the last thing, which is that I get sum over the routings of sign of the routing, weight of the routing. Okay. And so if I put my assumption that the routings have to go from SI to TI, then this is the identity permutation, and I just get the sum of the routings. Okay. Now, if you have a situation where you might have routings that are not straight shots like this, then this theorem is going to be true, except that you're going to have signs according to the permutation of the routing. Okay? And in particular, that means that the result might not be positive. Now it can be a sum of positive and negative things, and so we don't know the sign of this. But the statement is still true like this. Okay. Let me make a very brief comment about the cycle situation. So what if you do have cycles? Well, if you do have cycles, the thing is that you can't count the number of paths, right? Because there's infinitely many paths. You can go around a cycle as many times as you want. So how do we do that? Well, in the weighted situation, this does make sense actually, because if you go around the cycle, and let's say the cycle has weight r, then if you go around again, it's going to be r squared. If you go around again, it's going to be r cubed. And as long as r is less than 1, that you can actually sum r plus r squared plus r cubed, etc. And you're going to get 1 over 1 minus r, right? Mm-hmm. And so with no cycles, this theorem can make sense as long as you put weights that are less than 1, and then this all works out also. But yeah, I can't remember if there might be some issue of like winding numbers appearing in here. So if somebody's really interested in the details, you should talk to me and we can get the details straight. But the point is that there is a statement with no cycles as long as the weights are less than 1. Okay. So this is the Lindström-Gessel-Viennot lemma. And now we want to show some applications.
I have a quick question.
Yep.
I don't know if that's where you're going, but is this somehow related to what we were talking about at the beginning of class? Like the determinant of something?
Yeah, so that's why whenever I haven't erased anything, you know that it's coming back. So it's coming back, yeah. Now I want to answer this question. So I want to interpret this determinant as something combinatorial. Okay? And there's hope of doing it, right? I mean, it's a determinant of combinatorial things, and so maybe it counts routings in some graph. Now, if I want that to work out, then I somehow have to come up with a graph with special vertices Si and Tj, such that the number of paths from Si to Tj is this number. And if I do that, I'm going to be done. And so I'm going to carry out the following construction. So let's consider a 45-degree angle like this. Okay? This is the point 0, 0. And now I want to define points Si and Tj. Si is going to be 0, comma minus Ai. And Tj is going to be Bj, comma minus Bj. Okay, so I take my numbers A1 up to AN, and I put a point at this as A1, then A2, then A3, so on, AI, so on, until AN. Okay, and the point is that these distances are A1, A2, etc.
If you meet S.
Oh yeah. Sorry, yes. S1, S2, S3, SI, etc. Okay? And I'm going to do the same thing now along the diagonal and call these points Tj. So T1, T2, so on, Tj, so on until I get to T10. Okay? And again, the point is that this distance is B1, this is B2. I mean lattice distance, right? And you should be thinking that there's a grid here. Maybe I'll even draw a grid so that let's see what this should be. So that's a drawing. And now I'm going to consider this as a graph where the edges are oriented up and right. Okay? Orient edges up and right. So you're only allowed to walk either up or to the right. Okay? Now, how many paths are there from Si to Tj? If you want to get from Si to Tj, then, because you're only allowed to go up or right, you basically have to find a path inside this box, right? And you just look at any grid path from this point to this point. Okay. Now, how many paths are there here? Well, how long is this? This is, remember, this is a 45-degree angle, right? And so this is Bj, so this is also Bj. And how long is this? Well, this is Ai. Sorry, from here to here, it's Ai. And from here to here, it's Bj. So this distance is Ai minus Bj. This is Bj, and this is Ai. So I get that. Okay? So that means that number the number of paths from Si to Tj is what? Well, to go from here to here, I need to take Ai steps, Bj of which are right. I need to take Bj steps to the right and Ai minus Bj up. So the number of ways of doing that is Ai choose Bj. So the number of paths from here to here. Just a simple binomial coefficient. And therefore, my determinant that I'm trying to understand is just the number of routings from S to What does the routing look like? Again, you have these points here. Let's say there's 5 of them, and then you also have 5 here. Okay. And so what you're doing is you're counting the number of ways of routing these points to these points. Okay. And here you can see that you do have to map SI to TI, right? Because if you map SI to something bigger than TI, then you're going to have to form a crossing. So you're looking at the ways of walking from here to here, from here to here. Like that. And that's precisely what that determinant counts. Okay. And so this is a very simple, or I don't know if simple, but it's a very elegant description of why this number is positive. It counts precisely the number of ways of routing some points here to some points here. So this is the result due to Gessel and Viennot to interpret these determinants. Okay. One, two, to AM, B1, B2, up to B. Okay. And so so now what I want to do is discuss a few instances of this fact. So, example. Let's consider a determinant like this. M choose 0, M choose 1, dot dot dot, M choose n, then m plus 1 choose 0, m plus 1 choose 1, dot dot dot, up to m plus 1 choose n, and so on, until m plus n choose 0, n plus n choose 1, up to n plus n. Okay. So that's some determinant, and maybe for today it would have seemed inconceivable to try to figure out what the determinant is in some. I mean, at least it would seem like you would need to do something very creative. Here we don't have to be creative anymore because we know exactly what this counts, right? What does this count? It counts some kind of routing, okay? Because here the AIs are m plus 1 up to m plus n, and the BJs are 0, 1 up to n. And so let's just draw this problem and figure out what we're trying to count here. Okay, so I think I don't need this anymore. So it's the number of routings in a problem that looks like what? Well, like I said, the AIs are m plus 1 up to m plus n. And the BJs are 0, 1, until n. So I need to route these guys to these guys, and the question is, what are the ways of doing it? So how would you get started in trying to route these guys to these guys? There's something that's forced, right? Which is that, I mean, remember you this is important and I didn't write it here. The edges have to be oriented up or to the right. You're only allowed to walk up or to the right, which makes this an extremely restrictive problem, right? So if you were going to get to 0, you can only get to 0 from here. So you have to route this guy up. Okay, now what about the next one? Well, you want to make sure that it doesn't hit the other one, so you have to go to the right. Okay? And once this guy goes to the right, nobody else has access to 1 except for him. Right? Anybody else that tried to go up to 1 would have to hit this guy. So the only way to do it is for this guy to go to 1. And then this guy, you don't want it to collide with this, so you have to walk all the way up here. And again, once you get here, you block the access of all the other ones below you to get to this point, and you're the one that has to go up here. Okay? And so on. You see that actually there's a unique routing which looks like this.
The answer is 1.
So the answer is 1.
That's a complicated one.
It's you could call this a complicated one, or you could call it a very simple determinant, or deceivingly simple determinant, right? You would never look at this and think that this is 1, okay? But you know that's a proof. And it's a very simple proof actually once you're familiar with this machinery. Okay. Let's do another example. What about this one? S1 choose 0, S2 choose 0, up to n choose 0. S1 chooses 1, S2 chooses 1, n chooses 1. So on, up until S1 chooses k, S2 chooses k, until n chooses k. Okay. This is the one that we started class with, right? This is the number of permutations n with descents at S1, Sk. So you have these descents and you have no other descents. Okay? So we already proved this formula, but now we also have an interpretation of this in terms of lattices. Okay, so this is also the number of routings in some other problem. Okay, so actually, I think I did an example last time where these guys were 1, 3, 5, and 8, and n was equal to 9. So I want to do the same example. So now, again, I guess this is actually the transpose, but it doesn't matter because the determinant and a matrix and its transpose have the same determinant. Okay. And so now I'm going to say the sources are S1, S2 up to n. Okay. So here's the sources: S1, then I skip 2, and 3 is the source. I skip 4, 5 is the source. I skip 6. I skip 7. 8 is the source, and 9 is the source. S1, S2 up to Sn, up to n, I'm sorry. And the sinks are 0, S1 up to Sk. Okay. So this is S1, S2, S3 up to n. And the sinks are 0, S1, which is directly to the right of this one, right? S1, S2, S3. So actually, maybe it's worth drawing a bit. Okay. I guess I'm never going to touch this part because the last sink is SK. And so what I have to do is that I have to route these guys to these guys. Okay. So let's try to do that again. My first step is force because I need to get to 0. And the only guy I can get to 0 is this one. Okay. Now to get from this guy to this guy, actually there's several ways. So I don't know. Here's one way. To get from here to here, I guess I can go like this. To get from here to here, I guess I can go like this. Okay. And to go from here to here, I guess I can go like this. Okay? So the Lindström-Gessel-Viennot lemma tells us that this determinant counts these routings. Okay. So what does that mean? Well, that means that there must be a bijection between these pictures and these permutations. Okay. I mean, at least they have the same number, and so that means there is a bijection. But of course, we would like a nice bijection, a combinatorial bijection. Okay. And so, given that I'm out of time, maybe this will be something for you to think about. This is a good discussion maybe to take to the forum. If anybody can find a bijection, I think it's a really beautiful problem, and it's not so easy. It's an interesting problem that you should spend some time on. To find a bijection between these routings and the permutations of n with a given descent set. So this question, find a bijection. So that's kind of interesting because the method gives us a new combinatorial fact about the equality of these things, and there's stuff, there's interesting information hiding there that you can uncover. So I think that's a good place to stop. But next time we're gonna do a little bit more stuff with this Lindström-Gessel-Viennot lemma. But yeah, we'll stop here. Question?
Just curious for that question. Earlier when you were doing this stuff, you said each like path corresponded to a permutation. You were doing the determinant. Is that kind of like maybe permutation?
Oh, I see your so we did talk about the possible permutations of a routing. Because it might be that in these routing problems, it could be that there is a way of getting the sources to the sinks in a way that's not in an order that's not the obvious order. But in this case, actually, if you think about it for a little bit, you can convince yourself that there is no way. You really have to map the first one to the first one, the second to the second, third to the third. And so it's not that permutation that comes up. You need some other place to find a permutation in this picture. Try it out. I'd love for somebody to discover this.